In manufacturing and production, analysts use the mathematical concept of finding the optimum value of a function to determine the ideal production rate. Hi, my name is Jason Rosenberry, and in today's lesson we are going to investigate maximum and minimum values of functions. Let's start with a definition. Absolute extreme values. Let f be a function with domain D. Then f of c is the a absolute maximum value on D if and only if f of x is less than or equal to f of c for all x in D. Or b, absolute minimum value on D if and only if f of x is greater than or equal to f of c for all values in D. Absolute maximum and minimum values are also called absolute extrema. There are also extreme values we call local or relative extrema. Let's take a look at their definition. Local extreme values. Let C be an interior point of the domain of the function f. Then f of c is a local maximum value at c if and only if f of x is less than or equal to f of c for all x in some interval containing c. Or b, a local minimum value at c if and only if f of x is greater than or equal to f of c for all x in some interval containing c. A function f has a local max or local minimum value at an endpoint c if the appropriate inequality holds for all x in some half-open domain interval containing c. A local max or minimum occurs on some small interval containing c. An absolute maximum or minimum is determined by looking at all the domain values. In order to use these ideas, we need a way to determine what values might be maximums or minimums. Theorem 2. The local extreme values. If a function f has a local maximum value or a local minimum value at an interior point c of its domain, and if the derivative of f exists at c, then the derivative of f evaluated at c equals 0. We will call these numbers critical points. Let's define that clearly. Critical point. A point in the interior of the domain of a function f at which f prime equals 0 or f prime does not exist is a critical point of f. So summarizing, extreme values, meaning maximums, minimums, extreme values occur only at critical points and at endpoints. Let's try an example. Use analytic methods to find the extreme values of the function on the interval and where they occur. So here we have the function f of x equals 1 over x plus natural log x, and we're looking at values of x between 0.5 and 4 inclusive. Let's start by finding the derivative of f. So f prime of x would equal the derivative of 1 over x, which is negative 1 over x squared, plus the derivative of natural log x, which is 1 over x. We can simplify this derivative. F prime of x is equal to x minus 1 over x squared. Now, extreme values happen at either an endpoint, so we have two endpoints given. We have positive 0.5 and we have positive 4 given. Those two are endpoints, so we have those two values. But also extrema could happen at critical values, values that cause the derivative to either not exist or equal 0. So let's set the derivative f prime of x equal to 0. So 0 equals x minus 1 over x squared. We see that we have two critical values. X equals 1 would cause the numerator to be 0 causing the fraction to equal 0. And we also have a critical value x equals 0, causing the denominator to be 0, which would cause the derivative to not exist. Now, of those two critical values, and I'll list those here to the right, so our two critical values, we have x equals 1, x equals 0. However, 0 is not in the interval under investigation. So we can throw that critical value out. So we have three values of interest: positive 0.5, positive 4, and also positive 1. We will now plug these values back into the function to see what type of range values or function values we get. So here I've set up a table of values. We have the two endpoints of our interval, 0.5 and positive 4, and we have the critical value, x equals 1. We substitute those values back into the function to get these corresponding range values. When x is 0.5, we get 2 minus natural log 2, which is about 1.31. When x is 1, f of x is 1. And when x is 4, f of x is 1/4 plus natural log 4, which is about 1.63. 1.63 is the largest value. So this is the maximum function value in the interval 0.5 to 4. 1 is the smallest value. So this is the minimum function value on the interval. What's going on at x equals 0.5? Well, 1.31 ends up being a local max value. What's happening is if you were to look at the graph of f of x at x equals 0.5, at x equals 0.5, you will see that that part of the graph is a place where we reach a peak and then start decreasing again. So that is what we call a local max value, not the overall max value. That is 1.63 on the interval 0.5 to 4. Let's try another. Use analytic methods to find the extreme values of the function on the interval and where they occur. We have f of x equals x to the 2/5 power, and we're investigating on the interval from -3 to 1 inclusive. So we have our function f of x equals x to the 2/5, and we have our closed interval from -3 to positive 1 that we're looking for extreme values. Let's begin by finding the derivative. So f prime of x would equal 2/5 times x, and now we take 2/5 minus 1, or minus 5/5, giving us -3/5. And now we want to try to find values such that the derivative, f prime, is either equal to 0 or undefined. And if we take a look at the graph of f, the graph of f looks something like such. And as you can see, there's a cusp at x equals 0. So there is a place where the derivative does not exist and x equals 0 is in this interval. So we must evaluate f at three critical points. We will evaluate x equals the left endpoint, -3, the critical point, the value that makes the derivative not exist, 0, and the upper endpoint, positive 1. So f of -3, f of x, f of -3 would be -3 to the 2/5 power, which is approximately 1.55. F of 0 is 0, and f of 1 is 1. So in the interval from -3 to 1, we see that we have a max value at -3, and we have a minimum value at 0. And you can confirm this by looking at the graph. We can see that here's the graph of f of x, and we're looking in the window from -3 to positive 1. And as you can see, at 0, the function reaches its minimum value of 0. And again, at the two endpoints at -3, this function value, which is 1.55, is larger than evaluating the function at 1, so we get the largest possible function value from -3 to +1 to be 1.55. Identify the critical points and determine the local extreme values for y equals x times the square root of 4 minus x squared. Let's look at the graph. Here we have the graph of y equals x times the square root of 4 minus x squared. And from the graph we can see that we seem to have a local max value here at x equals -2, and that value is 0. Over here it looks like we have a local minimum value of 0 at x equals +2. What we're interested in are where are these 2 points? Where are these 2 points? Here we have an overall max value, and here we have an overall or a minimum or an absolute minimum value. So let's go through the process to try to come up with what those values are. So let's start by finding the derivative. So if y is equal to x times the square root of 4 minus x squared, calling this f of x, then f prime of x, using the product rule, would be first x times the derivative of the second. So the derivative of square root of 4 minus x squared would be 1/2 times 4 minus x squared, that quantity to the -1/2, and then we got to take the derivative of 4 minus x squared, giving us a factor of -2x. So there is first times derivative of the second plus the second function, square root of 4 minus x squared, times the derivative of the first, or derivative of x, which is just 1. Now let's simplify a little bit. We have f prime of x equaling, looks like we have these two factors of 2 would divide out. So it looks like we have a -x squared over the square root of 4 minus x squared plus this guy here. So to get a common denominator, we're going to multiply top and bottom of this by the square root of 4 minus x squared. So in doing so, we would get a 4 minus x squared over the square root of 4 minus x squared. We can now combine these two together in one. So our derivative, f prime of x, would equal -x squared plus another -x squared would be -2x squared plus 4 over the square root of 4 minus x squared. So there's f prime of x. Let's now set our derivative equal to 0. So we have 0 equals -2x squared plus 4 over the square root of 4 minus x squared. And the only way for a fraction to equal 0 is if this numerator equals 0. So setting the numerator equal to 0 gives us the equation 2x squared equals 4. So dividing both sides by 2, we get x squared is equal to 2. X is equal to plus or minus the square root of 2. Therefore, we have a maximum value at x equals root 2, and we have a minimum value at x equals negative square root of 2. We can confirm this result by again looking at the graph. We have stated that there are local extrema at x equals plus or minus the square root of 2, which means x is approximately equal to plus or minus about 1.41, and as you can see it looking at the graph, at positive 1.41, which is about right here, we have our local maximum value, and at negative 1.41, which is right about here, we have our local minimum value. Now it's time for you to try a problem. Identify the critical points and determine the local extreme values for the following: y equals -x squared minus 2x plus 4, when x is less than or equal to 1, y equals negative x squared plus 6x minus 4 when x is greater than 1. Pause the video while you work on this problem. When you are finished, restart the video to check your solution. Okay, let's consider the condition of x being less than or equal to 1 first. If that's the case, then f prime of x, the derivative, ends up being negative 2x minus 2. Setting that derivative equal to 0, so we got 0 equals negative 2x minus 2. We see here we get a critical value of x equals negative 1. F of negative 1, plugging negative 1 into our function, f of negative 1 is 5. So we know that when x is negative 1, f of x is 5. Now let's investigate the second condition when x is greater than 1. When x is greater than 1, then our derivative will be negative 2x plus 6. Setting this derivative equal to 0, negative 2x plus 6, subtracting 6 from both sides and dividing by negative 2, yields the critical value x is equal to 3. So when x is equal to 3, f of x is equal to 5. Therefore, we have a maximum function value of 5 happening at two places, happening at negative 1 and also positive 3. There is also one other critical point that we must consider. Notice right here that the derivative of y would not exist at x equals 1. Therefore, x equals 1 would also be a critical value. So let's evaluate y when x is equal to 1. And plugging 1 into the function, we need to use the top rule, and evaluating this at 1, we would get a function value of 1. Therefore, there's a maximum value at negative 1 of 5, there's a maximum value of 5 at positive 3, and there's a minimum value of 1 at x equals 1. In this lesson, we explored the critical values, maximum and minimum. Be sure to work the exercises that your teacher assigns. We'll see you next time.